So we'll look at this matrix, and because the next step which I will do will be this step. I didn't type this in, just the software helped me a little bit. So the conversions which we did are these ones. So we subtract 2 row 1s from the second one, and we subtract 1 row 1 from the third one, and that vanish these 2 elements. The next set of operations which I was suggested by the software is this one. We add 2 of seconds to the double of the second row to the third row, and that's the result of that. That vanished this element. This is already the row echelon form. At this stage, you already can make a decision whether your requirement, this requirement, is met. Because if at this stage you ended up with not every pivot on the left-hand side, this condition is not met. But this time you see the condition is met. We have all 3 pivots on the left-hand side. So we can go on to the reduced row echelon form now. The set of operations which I need for that, we have to do this. We have to put negative next to the last row. That's the result of that. We have to triple the last row and add to the second one, and we have to triple the last one and subtract from the first one. That will vanish these two elements. That's the result of that. Only one step left. We have to vanish now these 2. The operation required for that is this operation. And the result of that is this. This is a set of operations from up here down to here, which is mentioned here, which is concealed by these dots in this particular example. And this set of operations, we did this set of operations on each of these basis vectors E1, E2, and E3, and the result of that, here it is. This is my inverse. The inverse for this matrix is this one. We will double check it in a second that it's truly the inverse, but that's how the process goes. It is a computationally intensive process. It's not a surprise. In fact, in every problem which involves maybe not in every problem, but in many problems which involves matrices, and many of these problems are very computationally intensive. All this computational intensity, it comes from the necessity of computing the inverses. For instance, it's a very good example actually. In your computers these days, in this computer for instance, they have a special unit which is called the graphic card. Some of you who computer aware maybe know about that. The hit this graphic card works out every time you play a game on your computer is just because this graphic card computes lots of inverses of matrices. That's the main computational task of this cards to compute the inverses, because in all of, for instance, in the question of light propagation, the way it's like for it reflects from the surfaces, something which impresses you when you play a great game, right? Where you see all of these blurs and everything. Inverses are very important there. I mean, some of you who will study optics later, you will realize inverses of matrices is something you can't live without. It is a computationally intensive process. You will need to demonstrate us that you will pick up the idea, and you have to do this computation by hand a few times during the test and the exam. You have the solution helper for that. You have Maple for that. Maple can help you with that. But still, on a few occasions, you have to do it by hand, and you have to practice that. You have to practice that. Now let's just double check that this is indeed the inverse. So here's my A matrix, the one which I had before. Here's the inverse. Here's the suggested inverse, and this is the identity. I'll just put these 3 together because I want to do the double check. Let's just do the double check. So look at this. If I take row here, and if I multiply this row with the column here, that will be the result. Result will be this element. Let's just see if this is truly 1. 1 times -40, -40. 2 times 13, 26. 3 times 5, 15. -40 plus 26 plus 15, 1. What about this element? What about this element? Oh, gee. No, this lost focus. What about this element? So I'm looking now at this row and this column. 1 times 16, take 10, take 6, 0. What about this combination? 9, take 6, take 3, 0. What about this combination? This combination will give me this element, right? This combination will give me this element. 2 times 9, 18. Take 15, take 3, 0. What about this element? Yeah, I know, it's like a, yeah, we should come up with this. It's like a, you might think it's not a big surprise, but think about the process which led to this. If you try to do it directly without this structuring, I think you will get lost in the way, like 10% or 10% of the way, because it's really complex task to find the inverse. Even for computers, it is a complex task. With the light propagation, they operate with the 4 times 4 matrices only. They don't talk about the matrix like a million components or something. No, they don't. They just look at the matrix of with the light propagation. It's a 4 times 4 matrix all the time. It's nothing else. Just 4 times 4 matrix, and you need this huge, expensive hardware to do that. Anyway, we can also check the other way around. So we just checked with you. Like something like this, right? We multiply A by the A inverse from in this order. We can also check in the other order. So we have to, in the other order, we have to take rows from here and columns from here. Let's just see this, whether this hits 1. This one. Negative 40, it's a different combination, by the way, right? It's negative 40 plus 32. 2 times 16 is 32. And 9 times 1 is 1, right? Yeah, it's still 1. And this way, this element will appear if I take this combination, right? This element will appear in this order of the product. If I take this combination, 13 times 1, 13, take 10, take 3, 0. You can finish this double check, and actually, I strongly encourage you, when you do computation of inverse, it's a computationally intensive process. You will make mistakes computational in the way. You will, trust me. I make mistakes, even though I did it lots of times. You have to double check yourself, because if you won't, your effort will be wasted, and on some occasions even marks will be wasted. So please don't be lazy, do double check, okay, like I'm doing right now. So the last thing about the inverses, this requirement, remember the main requirement which enabled the whole process, this was this requirement. You may ask what will happen if this requirement is not met. If this requirement is not met, it means that not every column on this side in your row echelon form will be the leading one. So on this occasion, you might have 2 outcomes. If you still have the leading column here, you have no solutions. If you don't have the leading column there, you have multiple solutions. So the question is whether we have the inverse when this is not met. The answer to that question is, well, you see, the thing which actually ruins, you want to say no, of course. I want to say no too. Yes, the answer is no. But it's not. It is not really straightforward, because, like I said, if this one doesn't have a leading element there, if this is not a leading column, you still have solutions. So why the answer is no? Well, it's a deep result, it's a deep mathematical result which says that actually out of one of them may not be a leading column, but out of these 3, one of the right-hand sides will always be a leading column. Maybe not all of them. Some of these will have a solution. Maybe this will have a solution. Maybe this will have a solution, multiple solutions. But at least one will fail. So in combination, if this is not met, in combination, you will not have a solution in combination for 3 of them. And that's why if this condition is not met, you do not have the inverse. It's a deep result, and it's not so obvious, actually. So I said it's a theorem which says inverse exists if and only if this reduced row echelon form is the identity matrix, which is the same way as, I can equally say that if this reduced row echelon form has every column leading one. Right. Any questions? Yes?
So you can't take the inverse of a non-square matrix, then?
No, you can't, because it's not because of the sizing. No, it's not because of the sizing, because you can probably think of a matrix of a proper size which you can multiply with A. This is true. But the problem you will hit problems here. This condition will never be met for the non-square matrix. Condition is not met. Yes?
So with the condition that every column has to be leading at the end, that is are there matrices that are square that don't have inverses?
If this condition is not met, they don't have the inverses. Yes.